Well, I've had a great couple of days so far, but one of the consequences of all the great conversations that I had yesterday was that I found myself saying to 3 different people, oh, I wasn't going to talk much about that, but I'll add it to my slides. And then last night, of course, as I was adding things to my slides, I realized I also had to take something out. So I'm going to say a little less about nuclei than I was planning, and a little more about nucleons, and a little bit more about machine learning algorithms. So the titles changed slightly from the abstract. All right. So I want to talk about the role of gluons in the structure of hadrons and nuclei. And of course, the simplest questions we can ask is how much do gluons contribute to the simple static properties of particles like the proton, to mass, momentum, spin. We can get a little bit more detailed and talk about the 3-dimensional distribution of quarks and especially gluons inside the proton as encoded in various distribution functions, form factors, and so on. And I'll talk in particular about gravitational form factors today and about the Collins-Soper kernel, which is the same rapidity anomalous dimension that Ian mentioned in his talk yesterday. He showed one of our results, and so I'll give you a little bit more how the sausage was made on that front. And about the role of quarks and gluons in the structure not only of protons, but of nuclei. And so especially thinking about gluons, of course, gluons bind the quarks and gluons into protons and neutrons, and the way we like to model nuclei is as a collection of modified protons and neutrons stuck together, right? But really, I want to talk about how the gluons contribute to the binding of the nucleus as a whole, how it's different from our effective models of nuclear structure as protons and neutrons together. Okay. Now, something I want to emphasize here is that this is a really, really exciting time because our understanding of the role of gluons in hadron structure is evolving on both experimental and theory sides simultaneously. And so I like to think of this as being the QCD down understanding of confinement is improving at the same time as sort of the theory model up understanding of confinement. And so from this sort of top-down perspective, even in QCD where we can do experiments, it's only now that we're starting to get insight into questions, qualitative questions, like this one. What is the gluon radius of the proton as compared to a quark radius? So if you go and look up in the PDG, the proton's radius, you'll get the charge radius, which is the radius as seen by an electromagnetic probe, which does not couple directly to gluons. Right? And so then you say, okay, well, what about the gluon radius of the proton? Do I like an MIT bag model where the gluons expand to fill the bag and you get a larger gluon radius? Do you like a constituent quark model? The gluons hide inside massive quarks and you get the same quark and gluon radii. Do you like flux tubes and lattice QCD with heavy quarks where you pull them apart and the gluons are always between the quarks and so you get a smaller gluon radius? Which of these kind of pictures do we have? Okay, this of course depends on precisely how I define what I mean by a gluon radius compared to a quark radius. And so that brings us to the various distributions we use to define the proton's 3-dimensional quark and gluon structure. So here's our proton, and that there is one of the partons, a quark or gluon. The simplest thing we can write down is the parton distribution functions. Is there? There is a stick. The parton distribution functions, so the number densities of quarks or gluons of some flavor in some hadron, say the proton, carrying a fraction x of the longitudinal momentum of the proton. So the proton's coming here with momentum p. This parton's carrying some fraction x. Okay, we can go to the transverse direction also, have some transverse momentum kt, then we get the transverse momentum dependent parton distribution functions. We can go further in impact parameter space also, take a Fourier transform to get the generalized parton distribution function. So this delta squared, that's a squared momentum transfer related by Fourier transform to the impact parameter. The psi, that's just the skewness or a longitudinal component of the momentum transfer. Okay, so I'm going to start with aspects of GPDs, which will give us some insight into this radius question, and then come to aspect of TMDs, which will relate back to Ian's talk yesterday on the rapidity anomalous dimension. Okay, and so the perspective I'm taking here is, as I said, top-down, starting with QCD, and first principles calculations thereof using lattice QCD. And much like Michaela yesterday, I'm going to say very little actually about lattice calculations themselves, other than to say that this is the non-perturbative first principles approach to calculating QCD. I take the theory, discretize onto a Euclidean four-dimensional space-time grid or lattice, and then solve the path integral numerically. And so there's some non-zero lattice spacing, some finite volume. It's a lattice theory. I have to extrapolate that spacing to 0 and that volume to infinity to connect to continuum infinite volume QCD. Sometimes one might use larger than physical values of the quark masses. That's particularly true when I talk about nuclear structure, because that makes the computations cheaper, and when we're really pushing the boundary of what's possible computationally, that's a very easy crutch. But effectively, all we're doing is taking, quite literally the QCD path integral, but now in Euclidean space, so I have no I in front of my action here, and computing it numerically using Monte Carlo. And I'm emphasizing this because when I come back and talk about algorithms at the end, I'm going to talk about this particular Monte Carlo a little bit more. But so if I sample gauge fields according to this weighting with the exponential of the action, that's my important sampling approach, then at the end I'm taking just this operator that I want to compute it on each of those samples, and essentially means and standard deviations over those give us that observable and the expectation value that we're trying to compute. Okay, so something that I think is always important to emphasize, especially when I start talking about nuclei, is this is really just a numerical approach to the QCD path integral in a Euclidean spacetime, right? Once the free parameters are the same free parameters as in QCD, so the quark masses and the strong coupling. And so I sacrifice some number of experimental measurements that I use to tune those parameters and match them. So I use the pion mass to set one of the light quark masses, right? And once I've done that, everything else is a prediction of the theory. And so especially when I get to talking about nuclei, there is no sense in which I have to model a nucleus as a collection of protons and neutrons. Protons and neutrons don't appear here anywhere. I just write down the QCD path integral with the right quantum numbers for the nucleus, and I calculate it, right? And so everything else from details of the proton structure through to details of nuclear structure or nuclear interactions or reactions are just computed from path integrals directly. There's no modeling involved. Okay, so coming back to the generalized parton distribution functions, and I want to talk in particular about the generalized form factors, also known as the gravitational form factors. So known as gravitational form factors because they are what would encode graviton scattering from a nucleus, just like the electromagnetic form factors tell you about electromagnetic scattering from a nucleus. Of course, experimentally, we don't do graviton scattering. We use 2 photons to mock up a graviton, right? And that's how you get at it. But the GPDs are defined here. So I'm talking about gluon structure mostly in this talk. So here I have 2 gluon field strength tensors. This is my, say, proton with some momentum and some spin. This is a Wilson line in between them, right? And if I write down this, I have some number of different Lorentz structures that I can write down. Here my spinners are the U's, right, nucleon spinners. And in front of them, I have some number of a priori unknown coefficients which encode the non-perturbative structure of, in this case, the nucleon that I'm probing. Those are the generalized parton distributions functions, these a priori unknown coefficients in front of the Lorentz structures. If I take moments of those, so integrate over x, which is my longitudinal momentum transfer here, I get, again, some a priori unknown things. These are what are called the generalized form factors or the gravitational form factors, and those are what show up if you do graviton scattering. Now, this definition is, doesn't give you the intuition on exactly what these encode, so let's look at them another way. You get these same gravitational form factors or generalized form factors if you write out matrix elements of the energy momentum tensor. So here, this is just my gluon traceless energy momentum tensor. Again, my proton with some momentum and spin. There's some momentum transfer, so p minus p prime squared is what I'm calling t here. That's the squared momentum transfer. Again, I write down my sort of different Lorentz structures and coefficients out the front, and these are these same GFFs, which stands for either gravitational form factor or generalized form factor, depending who you ask, that appeared as moments of the GPDs themselves. So here, as matrix elements of the energy momentum tensor, you can really sort of get intuition for what they encode. So if we go to the forward limit, so no momentum transfer, and take this A GFF here, this is just precisely the momentum fraction carried by different partons inside the proton. So this tells you what fraction of the proton's momentum is carried by up quarks, down quarks, gluons, strange quarks, and so on. Of course, there's a sum rule that it has to sum up to 1. A combination of A and B does the same thing for the spin. What fraction of the proton's spin is carried by up quarks, down quarks, strange quarks, gluons, and so on. So that takes care of A and B. There's also D. And so this was, it enters the equations in the same level as momentum and spin, there's no sum rule. It's called the D term. And this was a far less known, but in some sense equally fundamental aspect of proton structure. If you want to have intuition on what this D term encodes, through this being the energy momentum tensor, you can again get some intuition on that. There is a sense in which you can interpret Fourier transforms of this thing as telling you something about pressure and shear. There's a bit of debate about whether you should really identify these things as pressure and shear, and I don't really want to get into that. The motivation is really through this being the energy momentum tensor. It's a very clear connection. What it is mathematically well defined. What we call it is another question. Okay. So these D terms, it's really been a story of the last 5 years or so. They were first constrained experimentally at all for the quark D terms through deeply virtual Compton scattering at JLab in 2018. And so this is this D generalized form factor. This is the momentum transfer, and these 5 points are the constraint from experiment on that. If you define the pressure and shear distributions, again, through this identification with the energy momentum tensor, and you say, okay, this is just the quark piece that was constrained from experiment. Let's assume it's everything. Let's take these 5 data points and Fourier transform them. You know, there's a few sort of pieces in here that need to be refined, but you can write down a pressure distribution inside the proton. This is the center of the proton. This is the radial direction moving out from the proton center. There's some repulsive pressure, some confining pressure. This thing has to integrate over 0 for the proton to be stable, as we know it is, yeah? The energy momentum tensor contains both of them. Through deeply virtual Compton scattering, you're really accessing the charge squared weighted combination of the quark pieces and not the gluon piece. That separation is a little messy and scale dependent, and so writing down this thing as a total involved a number of assumptions, you know, that the gluons are just contributing equally, and so on. Formally you can write down the gluon piece of the energy momentum tensor and the quark piece and compute the mixing between them, which is what we've done from Lattice QCD, but it's a little more messy in practice experimentally, yes. But this is sort of a particularly nice part of the story, because from this it was seen for the first time that the pressure in the center of the proton is something like 10 to the 35 Pascal, which is a pretty nice scale, right? That's about an order of magnitude more than the inside of a neutron star, but it's about the same as in the quark-gluon plasma, and so you can really have this feeling of protons as being little drops of QGP, which is a nice picture. But okay, in about the same time as these experiments, we were very excited to be able to do the first Lattice QCD calculation of the gluon part of the GFFs, and particularly the D term, which let us see for the first time, by combining gluon part from theory with quark part from experiment and putting them together, be able to see for the first time what this GFF actually is. Neither theory nor experiment had both pieces, so it was only in combination that we were able to actually constrain both. And that's what you see here. This is this D-term generalized form factor. These 5 blue data points are the quark from experiment. This green is the gluon from Lattice QCD. You can see there's a factor of a few between them, but they're not orders of magnitude different. The shape is vaguely similar. And if you transform to this pressure distribution picture on this right-hand side, where this is the radial direction from the Fourier transform, the blue is the quark part, and the green is the gluon part, and you have a first hint at this question of a gluon radius. So defined in this way, from this pressure distribution, the gluons are extending the tail. So the gluons are extending that radial distribution of the proton. Now, there are many things lacking in this first comparison. There's one part from experiment, one part from theory. The theory calculation had larger than physical values of the quark masses. The mixing between the two wasn't properly accounted for. And so this was sort of, imperfect, but the very first hint of being able to answer this qualitative question of how does the gluon radius of the proton compare to the quark radius. And so, yeah.
Sorry, why would you even want to define such it sounds like a very ambiguous thing. So why even split quantities into gluon and quark contributions? Why not stick to something that is robust and measurable? What is the benefit of measuring this thing? Is it just for our sake to feel Like, we understand what a gluon and a quark is?
It's for our sake, and particularly in the context of this collaboration, it's to try to get some more insight into confinement, right? So I'm going to talk later about measuring these radii also in a glue ball. And so trying to really understand, does the gluon structure of a glue ball look different from the gluon structure of something like a proton? And try to pull apart, what makes bound states primarily of gluons different from bound states of quarks and gluons together. It's.
But I guess the question is, beyond some gauge invariant sort of like form factor, which you're calling gluon scattering or whatever, graviton scattering, what does it even mean to split the gluon from the quarks? I mean, either you have, what is the observable here? Is it just all model dependent? We cook up some model and a piece of it is gluon, a piece of it is quarks. I guess that's...
No, I mean, you write down in the previous slides matrix elements of the gluon piece of the energy momentum tensor.
But what?
So 2 gluon field strength tensors, or matrix elements of the quark piece of the energy momentum tensor.
Yeah, it's probably my ignorance, but I fail to see how that is a well-defined split.
Well, it's well-defined. It's just scale-dependent.
Oh.
Right? So it's much like a Parton distribution function, and the distribution of components of the proton's momentum depends on mu, right?
I think there was a lot of discussion of this in the context of so-called spin crisis of the proton. And in the end, I think it was people defined it carefully.
Yes, you can make different decompositions of orbital energy momentum, D decomposition or Jaffe-Manaha decomposition, and you can account for all the components. So I wouldn't call it model dependent. I would call it scheme dependent.
Okay.
And scale, of course. Okay, so the status of this is that we now have calculations with systematic control of all pieces of this from Lattice QCD, so we can really now answer these questions precisely. And so this is largely the PhD work of my excellent student, Dimitra, who's now a postdoc at Berkeley. Okay, and I'm not going to tell you about the details of how we got there. I'm going to show you some of the results. And so what you see here is this A generalized form factor and the J generalized form factor, and the decomposition into different quark and gluon components thereof. You can make the checks of this, of the sum rules, for example, in the forward limit here, this A is the momentum. Between them, all the quarks and gluons should carry 100% of the proton's momentum. They do. This should be the spin, should be 0.5. It is, right? So you can see that systematics are under control within the uncertainties shown. And we can go and look at the D term also. Yeah, and a first decomposition of this into quark and gluon pieces. Now, let me show you the comparison with experiment, which is where this gets particularly interesting, and then the comparison with other hadronic states. All right, so we can go back and compare, now that we have a lattice calculation of the quark D term, we can compare to the experimental measurements of the quark D term. And here we see, what's really making me enthused about this right at this moment. This is, again, the momentum transfer. This is this quark D term. That theory and experiment right at this moment are very complementary. Theory has much better constraints out here at large momentum transfers. An experiment has the kinematics that give us constraints here at the small momentum transfers. And so things are consistent. This gray band is including systematics from the experiment, but really providing constraints in different regions of parameter space. There's also a real feedback loop between theory and experiment at this time. So there have been now first measurements of the gluon generalized form factors from experiments. And what you see here is the A and the D gluon generalized form factors. The blue data points are from the lattice calculation, and the colored bands, the green, the purple, and orange, are 3 different analyses of the same experimental data. So that experimental data to essentially disentangle A and G requires some additional model input. And so different inputs that were put into that experimental analysis gives you these different curves, and you can see one of them agrees much more nicely with the theory than the other. So again, complementarity and feedback between theory and experiment. All right, and finally we can come back to this question of gluon versus quark radius of a proton. There are various ways of defining that. You can define from the energy density or from the longitudinal force density radii that are known as the mass and mechanical radii of the proton or other hadrons. And you have here quark and gluon definition of the radii that are completely analogous to one another, and so you can compare them in a very concrete way. And what you see here, this is the charge radius of the proton. The first thing you see is that the mass and mechanical radii by this definition are about the same, which is reassuring. The red here are the quark contributions, or the quark radii, and the blue are the gluon radii. These purple, green, orange, and green points are from the different analysis of experimental data that should be compared with this blue Lattice QCD data point, the one that we saw on the previous slide. This grey point came out about a week after my student's thesis result of this point from experiment, and it's perfectly consistent with the Lattice results. And so we see two things. First, we have theory predictions ahead of experiment. We're waiting for experimental measurements to compare here. And the second thing you see is that the blue points are further out than the red points, which means that even once we go and make this question more precise and the calculations rigorous, we have the same conclusion, that the gluons seem to act to extend the radius of the proton as defined by the energy densities and the longitudinal force densities. Yeah? These are at physical quark masses. Yeah, with mixing between the quark and gluon pieces accounted for and so on. Yeah. The one thing, the discretization artifacts here, it's done on a single lattice spacing. And the uncertainties include estimation of the discretization artifacts, which should be small relative to the statistical uncertainty, but that's the one thing that is not under complete control. Everything else is accounted for. Yeah. Okay, and then we can say, okay, now that we can go and rigorously calculate these form factors and associated radii, we can go and compare them for different hadronic and Glueball states. And so something that we're excited about that came out just last month is that we're able to, for the first time, calculate the radius of the scalar Glueball. This is in Yang-Mills. And so these are the gluon generalized form factors, the A and the D, for different states. We have the nucleon, delta, pion, rho, and the Glueball, scalar Glueball here in purple. And so what you see is, okay, the D is very noisy. The purple, it's considerably flatter, this A generalized form factor, than it is for the other hadron states. And when you translate that into a radius, what that gives you is this. So this is the mass radius of the scalar Glueball compared to other hadrons. This is combined quark and gluon. This is gluon radii that is considerably smaller. And so the gluon radius of the scalar Glueball is small. It is actually the most compact state in that channel. And what is very interesting about this is that actually this has been calculated or constrained before through beta salpeter wave function studies 30 years ago. And they estimated that the radius should be between 0.1 and 0.3 Fermi. And so this is, in fact, very consistent with those early works. Of course, we need to look a little further. This is in Yang-Mills. What about in QCD? We need to look at non-scalar Glueballs.
This is calculation without quarks, just pure Yang-Mills.
Correct. And we did the same thing for these. We calculated both in QCD and in the pure Yang-Mills setup, and all of the other hadrons are actually consistent. The gluon radii of those are consistent between Yang-Mills and QCD, and so we expect this not to be a huge effect on the other hadrons. What it is on the Glueballs, we still need to compute. And so those are the next questions. Is this a consistent feature? Are Glueballs always small? Is it just the scalar Glueball that's small? What does it mean, and what can we learn about confinement from this? Yeah.
There is some difference with inverse of that scale, I suppose. In that calculation, pure Yang-Mills calculation, which gives you that small scalar Glueball values, well, what's the scale of lambda Yang-Mills or inverse of it?
Oh, I think it's GV.
As compared to that scale, let's say, is there some parametric separation between inverse lambda Young-Mills and the size of the scalar glue ball?
Yeah, there is. The scalar glue ball is smaller.
Yeah, that's right. So,
Yeah.
so Arkady and his collaborators wrote that paper in 1982, if I remember right. It's called "Are All Hadrons Alike?" in which they made an argument that glue ball should have somehow higher scale parametrically as compared to lambda QCD. And he can talk better.
Yeah,
right.
Glueballs scales, when we say low meson channel, m square was 0.6 JV square. For Glueball channel, it was kind of 20 JV square or something. So numerical difference, not parametrical, but so in this way it's lambda QCD, but numerical coefficient.
Right.
So it's consistent with
It's consistent with this picture, yeah. Yeah, very nice. Okay. So now I want to move to talk about TMDs and specifically about the Collins superkernel, which is the rapidity anomalous dimension talked about by Ian yesterday, and tell you about QCD calculations thereof. Yeah.
Before you move on in the previous page, do I understand, can you compute this also for the value, for example,
Yeah, and we have those. I just didn't show the form fact. Well, I actually showed them on this previous slide. The pion is the blue here. Yeah, which we did both in QCD and in Yang-Mills, and they're consistent between the two.
The pion is also small.
Yeah, the pion is here.
The Glueball is even smaller than the pion.
The Glueball is smaller than the pion. Yeah, by a factor of 2. Yeah.
Can you use your seat mics, please?
I'm using this mic. Now it works. It has a delay. Could you help me understand conceptually what this pressure or the D term means? If I think about it as a pressure, conservation of energy momentum requires the time derivative of momentum to be equal divergence of the pressure or gradient of the pressure, right? So how could that be a ground state if the pressure is not homogeneous in the whole space? How do I think of that as a pressure without running into that contradiction?
Yeah. So what you need is the integral of this radial distance squared times the pressure to integrate to 0. Is what you need. So it's okay for there to be some repulsive pressure, but then there needs to also be a confining pressure, right? But it does depend on the frame that you look at it in. That whole plot that I showed of the pressure, that's a frame-dependent thing also.
And the fact that locally the gradient of the pressure is not 0 is not a problem? For this interpretation? Only the integral matters? I don't understand.
No, this is one of the reasons that people don't like it being called a pressure.
Okay.
Right? So it's...
Yeah.
But
I understand.
No, the quantity itself is well defined. The interpretation as a pressure is, yeah.
Okay.
Yeah.
But even if you do not call it pressure, there is still conservation of energy momentum. So it has to work in such a way that it's a ground state, but then it has non-zero gradient of the pressure. I don't know how you call it, stress tensor.
That's true. And so then there's a number of relations that you can write down between the GFFs and integrals thereof that must be satisfied, and you can go in and check that they all work numerically. But they're
Why does this gradient of the stress not create some motion? That's what I'm trying to understand.
Well, but there is motion, right? The whole thing's a dynamical system. It's
okay.
Yeah, I mean, so the sum rules.
The 0 point motion.
Some rules implement what you say.
Right. Okay.
So,
thank you.
Okay. So let's talk about TMDs. So we're moving from this sort of collinear parton distribution function picture to the transverse momentum dependent parton distribution function picture. And I want to talk in particular about the Collins-Soper evolution kernel, which is defined here, right? So it governs the rapidity evolution of the TMDs. So this is the rapidity anomalous dimension discussed yesterday. It's also needed for very pragmatic reasons. It shows up when you try to relate lattice calculable TMD constrained quantities to physical ones. So we need to constrain it for multiple reasons, and it's non-perturbative at long distances. And so it's a very natural thing to try to constrain from lattice QCD. Okay, so how can you do this? Which is one of the questions I got yesterday at lunch. So of course, what we're really trying to compute is something defined on a light cone, and I'm living in Euclidean spacetime. And so this has to be an indirect proposition, right? And so this has been over a decade of work now to try to develop all the formalism required to do this via what's called the quasi-TMD prescription, where what I would really like to calculate is matrix elements of, this is a Q and a Q bar, separated with these light cone Wilson lines between them. I'm in Euclidean space, so I can't do that. What I can calculate is matrix elements of this staple-shaped Wilson line operator with a Euclidean separation. And you can show that in the limit where the length of this staple becomes infinite and I go to infinite boost, that you can match this with a perturbative matching in a large momentum expansion. So this is a large momentum effective theory. And so then you can write down a relation between something that you can compute in lattice QCD, which is some finite staple length Euclidean separation of Q and Q bar matrix elements, and what I would really like to constrain, which is the TMD PDFs defined as they typically are. And so that matching comes with perturbative pieces, non-perturbative pieces. It comes with this Collins-Soper kernel, which governs the rapidity evolution. Okay, and there's been, yeah, like I said, over a decade of work now on defining how to do this perturbative matching, how to define the mixing in appropriate ways, and all of the formalism behind this. So getting at this Collins-Soper evolution kernel, you can do, oh dear, that slide has other things on it. Okay, well, that slide shows you how you can get at that Collins-Soper evolution kernel through the ratio of quasi-wave functions, which are these Euclidean calculable matrix elements. The soft function, this non-perturbative piece, cancels in the ratios, which is very convenient. But essentially, what you can take is the ratio of these staple-shaped Wilson line operators at two different, but both large, and extrapolate to infinite momenta. So the momenta need to be large and very different from one another. And in that limit, you can pull out the Collins-Soper evolution kernel up to perturbative matching and then power corrections in those momenta and in the lattice spacing and in lambda QCD. And so there are, yeah, so my apologies to the person I promised to show that slide to. I can show you after the talk. And so there are several steps to computing the Collins-Soper kernel from lattice QCD, which I'm happy to talk more about after, but I'm going to give you sort of the one-two skip a few here. Is you have to calculate these bare quasi-wave functions. You have to do a renormalization and matching, which involves both perturbative and non-perturbative pieces. Transform to momentum space, then disentangling the lattice spacing dependence from the power corrections requires simultaneously fitting to multiple different lattice calculations at different volumes and different lattice spacings in order to be able to do a continuum extrapolation. And so this is part of the PhD work of my other great student, Arthur, who's also just recently graduated and moved to Argonne. Okay, and so this is the sort of money plot that you saw yesterday in Ian's slides also, is that we've been able to do calculations with complete systematic control, so including continuum extrapolation, physical values of the pion masses, next to leading log matching, and this is this Collins-Soper evolution kernel versus my BT scale. Here in the perturbative regime, it agrees beautifully with perturbative calculations, and out here in the non-perturbative regime, you can see that the uncertainties start to become enough to differentiate between different phenomenological fits to experimental data of the TMDs. That became very real again with something just released last month, where we included these 20 constraints from Lattice QCD results into global fits of experimental data for TMDs. And this was actually really nice because we went back into the guts of the global fit. We did not take our continuum extrapolated Lattice QCD results. We took the raw Lattice data and did the global fit, including the various Lattice extrapolations as part of the global fit to the experimental data also. And what you see is that even just 20 constraints, because they are in this very important non-perturbative regime and directly on the Collins superkernel, reduce the uncertainty of the global fits by a factor of about 2, even though it's a very small number of data points relative to the experimental results. And so that's a nice example, again, of complementarity between theory and experiment at this particular moment in time. All right, and so then for the purposes of this talk, as I said, I'm focusing on gluons. So how do gluons come into this? Well, you can also look at the gluon Collins superkernel, or the rapidity anomalous dimension. And in the perturbative region, this is the same thing as the quark one, up to just a group theory factor, right? But what about the non-perturbative region? And there's just no information on this from theory or from experiment. And so we are well on the way to a Lattice QCD calculation of this. It is really challenging. I'll give you a feeling of the challenge here. So these are these quasi-beam functions that you can calculate from Lattice. Each of these points is the result of fits to a lot of Lattice data. And these two figures are for the same statistics for the quark case and the gluon case. And so you can see you need both orders of magnitude more data and much smarter approaches to be able to go and calculate this for the gluon case. But we will have first results out with, call them 20% level uncertainties in the next month or two. And I'd love to hear from anyone who is interested in this gluon Collins superkernel, also in other non-QCD theories, because I think this is interesting. We should talk more later, Ian. Okay, so I had to cut out a lot of the discussion I wanted to give about nuclear physics. So I want to make 2 points. I want to tell you firstly that in principle, you can go and calculate from Lattice QCD the structure interactions of the nuclei just like you do for protons and neutrons. But it is really, really computationally difficult. And the flavor of the computation, the noise, the statistical uncertainty grows exponentially with the number of protons and neutrons. So if you're thinking about Monte Carlo sampling, you have to do exponentially more, take exponentially more samples. And on those samples, you have to do factorially more work from all of the quark interactions. So you have an exponential times a factorial group in computational cost. I'm a member of a small but dedicated collaboration that for more than a decade has been working towards this goal. And I'd love to tell you about all of the latest and greatest advances on that front. But I'm going to show you instead an old result that I still think is quite interesting in the topic of gluons. So more than 35 years ago, my colleague Bob Jaffe and Anish Manohar wrote a paper that I think was underappreciated at the time about exotic glue. They called it nuclear gluonometry. So contributions to the binding of nuclei, gluonic contributions that cannot be associated with individual nucleons in the nucleus. So the way you can define this is through an exotic glue operator. So if you can write down a purely gluonic operator whose expectation value vanishes in a proton or neutron, but does not vanish in a nucleus, you in some sense have a measure of the binding, the confining of that nucleus that's not this picture, where the gluons all sit inside protons and neutrons that get pulled together. So something like this in the cartoon picture. So one such exotic glue operator that you can write down is the double helicity flip structure function. And just by virtue of being a double helicity flip, this is something that you can't do from a single proton, right? Spin half can't do a double helicity flip. And so this is something that vanishes in the forward limit by construction in a proton or a neutron. It's unambiguously gluonic. There's no analogous quark PDF at twist 2. It's non-vanishing only for something with spin greater than or equal to 1, so something like a deuteron or larger nuclei. And it's also potentially experimentally measurable, but that has not been done yet, although there are letters of intent to do so. So some years ago, we were able to calculate the first moment of this gluon transversity distribution in the deuteron from Lattice QCD, and this is not systematically controlled at all. So that's why I have no numbers on that plot, because I don't want you to read the numbers off and read something into them. But what you should look for is a bump of this very particular shape to the left of this red line, And what we can do is I get to play experimentalist and rule out the hypothesis of a no signal to better than 1 part in 10 to the 10 through this data. And so we can confirm that this effect does exist. And actually, if you do take these numbers at face value, which you shouldn't, but if you do, the magnitude is actually roughly what you would expect through large NC arguments. So there's a 1 over NC to the I minus j suppression that you expect of this relative to a generic spin-independent structure function in the deuteron as compared to some standard, more compact spin 1 thing like a phi meson. And so if you go and you calculate this for the phi meson and take the ratio of this to the momentum fraction and you take the ratio of this to the momentum fraction, you see, in fact, about the expected suppression here in this channel. So this is very interesting. There are no other constraints, experimental or theory, on anything remotely like this, and it can't be incorporated into standard nuclear physics models, which typically take modified nucleons to form a nucleus. Yeah?
Sorry, why isn't this related to stuff that people do in nuclear physics, where the difference between the nucleon matrix element and the nucleus is the off-diagonal elements of the nuclear level Hamiltonian? So nuclear, you know what I'm talking about? In nuclear physics, they model the nucleus as, as a mini nucleon state, and then there are interactions, there's some Hamiltonian that diagonalize that, and so couldn't you?
I mean, this is a purely gluonic thing, though.
But that also takes into account the gluons in the low energy effective theory for the nucleons, because they induce interactions between the nucleons.
Yeah, so, okay, in that sense, you can sort of, Raj, you want to say something?
Say something along these lines before, that you can actually measure exclusive hard processes or semi-hard processes like the phi or the j psi, where actually you see this effect which can never be explained by just looking at these low energy nucleon matrix elements. So it's clearly something like a Pomeron-like or multi-Pomeron effect. And I was going to comment that what you're saying is very interesting, because there are these collisions at the LHC of ultra-peripheral nuclei where photons interact with structure inside nuclei. And what you see is an interferometric pattern, which is like Henry-Brown twists, which is sensitive to this double flip structure that you just mentioned. And they see evidence of that in the data for exclusive vector meson production. So I think that's very interesting, what you mentioned.
Yeah. And
so
yeah. And part of my answer was going to be you could say that in calculation of things like spectra, this is in some sense accounted for and absorbed into the effective theory, but you can't go and try to compute this through any of those effective models, right? It's just not a piece that you can pull out.
Well, it depends what O is. What operators are you doing these plots for?
So that is this gluon transversity, so it looks like 2 uncontracted gluon field strength tensors. It's G mu nu G alpha beta, basically.
So you can really think about it as a double helicity flip of a 2-gluon configuration.
Yeah, like the diagram I showed before.
Yeah.
Okay, so this is the end of what I wanted to say about gluon structure from Lattice QCD, and we're particularly excited about Lattice calculations of the Collins superkernel, and especially the gluon Collins superkernel, and about the gluon gravitational form factors of hadrons and the scalar Glueball. And also sort of moving towards systematic control for nuclear physics also, and all of the opportunities that will open up. So this brings me to the sort of very quick part 2 of this talk, a little bit about machine learning algorithms, so picking back on Michaela's talk yesterday. So here, coming back to our sort of introductory slide on Lattice QCD, I'd mentioned that the first step of any calculation is to sample the field configurations distributed according to the exponential of the action. And this is a very large-scale sampling problem in something like 10 to the 12 dimensions. And among many other problems, this is one problem that we've been working very hard to improve using machine learning approaches. And so one of the ways you can try to improve the various problems with critical slowing down and topological freezing that you face in regular Hamiltonian or hybrid Monte Carlo calculations here is using what are called flow models, which you saw yesterday, as maps between probability distributions. So essentially we just have a change of variables from some initial distribution to some final distribution. And what makes this change of variables or this map a flow is that it's invertible with a tractable Jacobian, right? One that you can actually go and compute, and you can compute the inverse, and that it has many free parameters that you can optimize or train or learn, right? And then what the base distribution is, what the model distribution is, that is really up to you and how you're going to use it inside your workflow. So the sort of gold star dream would be to use this to do embarrassingly parallel direct sampling by using it as an approximate trivializing map. So in that case, the base distribution is something efficient to sample. Think high uniform on all of the links of a lattice. And the model distribution is your exponential of the action. If you can do this, you no longer have a Markov chain. By default, you just take independent samples of the base. You get independent samples of the target. You can optimize it, as was discussed yesterday, without having any samples from the distribution of interest at all. So you can essentially take a sample from the model, say with what probability was it generated, and with what probability should it have been generated, and minimize the difference. So you can apply this in regions of parameter space where you cannot do traditional sampling at all. And you can still guarantee exactness because the density is computable, so you can either reweight or you can form a Markov chain with an accept-reject step to guarantee all of the same guarantees of asymptotic exactness that you have with conventional sampling approaches. So this is the dream, and I've talked about this at previous collaboration meetings, so I'm not going to show you all of the history of work in this area, but this has many potential advantages: mitigation of critical slowing down and topological freezing, efficient parameter space exploration by retuning the trained parameters, direct access to the partition function, which you heard about yesterday. But this is only one of many approaches to using flow models for lattice QCD. And so we've been following various pathways, but what I want to mention today is by using the fact that you can generate in this way correlated ensembles and exploiting that. So accelerating sampling is not the only goal here. Accelerating physics is the goal, right? And so instead of mapping from a trivial base to a target distribution, you can map between two different distributions of interest. One thing that you could do is map between distributions where you've changed your action with a shift parameterized by some parameter lambda. And that then lets you do things like the Feynman-Hellman theorem, where what I say is, okay, now I go and compute the mass of some hadronic state and the derivative of that with respect to this additional parameter that I've added to the action. And if I compute this, right, the slope at lambda equals 0, that tells me the matrix element of that operator. So just differentiating through, essentially, having added this term to the action. That is very useful because this derivative here is something that you can do with a finite difference at different values of lambda. And if those ensembles that you're taking a difference of are correlated, you can significantly reduce the uncertainties on this matrix element that you're interested in. So especially for things like gluon structure, which are really, really very noisy, this can give you significant wins. You can also do two-point functions of things like Glueballs. This is a two-point functions from one-point functions kind of picture where we've done the same thing. We've added this parameterized shift to the action, and you can show that the derivative with respect to lambda of this thing gives you the two-point function that you're interested in. And so we can exploit all of this architecture that we've been developing over the last 5 or 6 years. And what you really need here is just diffeomorphisms on gauge field degrees of freedom that encode all of the various symmetries, so gauge symmetry, your rotations and translations with periodic boundary conditions that are flexible and expressive and can encode correlations at physically relevant scales. And once you have that, you can use it for not just accelerated sampling, but applications like the one I showed on the previous slide. Okay, so the sort of history in my research group's efforts on this front are here, that we've slowly built up from scalar field theory to abelian and non-abelian gauge field theories to fermions, to combining gauge fields and fermions, to dealing with pseudo-fermions, which is the approach we use because doing fermions is too computationally expensive, all the way up to initial applications to QCD in 4 dimensions. And we are now running on Aurora, which is the new largest supercomputer in early science time, attempting to deploy this at the scale of state-of-the-art lattice calculations. I'll give you a couple of Oh wow, this is also missing something on the slide. But nevertheless, you can see some of the part of the slide here. This is from a U1 field theory, so an example from a couple of years ago, where you can really sort of viscerally see this is the topological charge. This is a hybrid Monte Carlo, and this is a heat bath algorithm in the blue and the black, and you can see that they get stuck in topological sectors. That's why the line is flat. The orange is sampling from the machine learning, which just goes to all of the topological sectors very efficiently because it's not a Markov chain, right? So there's no connection from one sample to the next. And if you translate that into an integrated autocorrelation time, which is was also shown yesterday, you can see that conventional sampling becomes exponentially more expensive as we move to the right to smaller lattice spacings, whereas the flow remains reasonably flat. And so this is an example of sort of the various advantages of accelerated sampling. But in the last few years, we've also made first steps towards exploitation. So the first application to QCD, so 4 dimensions with fermions, was at very small scale in 2022, but you see beautiful agreement. Here's the topological charge, and you can see, of course, because you have asymptotic exactness guaranteed in this method, it should be no surprise that it agrees beautifully in regions of parameter space where you can do both conventional sampling and machine learned sampling. And then here, from last year, you see first exploitation for physics observables. This is using the Feynman-Hellman approach, so mapping between ensembles at different parameters. And this here is the forward limit of the A gluon generalized form factor. This is the momentum fraction carried by gluons in a pion. This is in a quenched QCD calculation from last year. These are the same statistics in a calculation using independent ensembles to do it the conventional way and using the machine learned ensembles. And you see it's an order of magnitude uncertainty reduction using this approach. Come to this year, we've now done the same thing, not in quenched QCD, but in QCD. QCD, in this example, the pion mass is slightly larger than physical. We're now running it at the physical point. This is, again, the gluon momentum fraction in the pion. This is a Euclidean time, so you can see sort of more clearly how the standard approach is both noisy and fluctuating, whereas the machine-learned approach has a factor of, say, 3 uncertainty reduction, so a factor of 10 on compute, roughly, is saved there. And for Glueball two-point correlation functions, this is in Yang-Mills, and related to some of the results I showed before, we have a factor of 40 uncertainty reduction. And what's particularly tantalizing is this here is the variance. No flow, variance with flow goes down by more than an order of magnitude. But the red is the variance of the flow if it were perfect, if you didn't have to correct for the inexactness of the flow at the end and reweight. And you see that is much, much lower again. So this is sort of a tantalizing potential that if we could train this optimally, you might have a potential for exponential uncertainty reduction. So this is exciting. These are approaching sort of reasonable scale volumes and pion masses. This is 12 cubed by 24, and now we're running at 32 cubed by 64, so approaching reasonable scales for these problems. Okay, so the sort of summary of this work is that we have these provably exact machine learning accelerated sampling algorithms that are orders of magnitude more efficient than conventional algorithms, overcoming critical slowing down in certain parts of parameter space. They're unbiased in certain regions of parameter space where the traditional approaches fail because they don't get stuck in topological sectors. And we're using them for qualitatively new calculational approaches exploiting features like being able to generate correlated ensembles. And we are deploying now at the state-of-the-art scale. So this sort of gold standard direct sampling from trivial to state-of-the-art, that we're not deploying at scale. That needs some more work. But between correlated ensembles at different parameters, we're now running that at parameters of the latest Glueball spectra calculations. We're now doing the machine learning approach at those scales. So this is starting to hit the prime time. Okay, so that is the end. Thank you.